Hello and welcome to another Ginger Mathematician video. Today we're going to go through all of A-level paper 1, trig identities and equations. Often a topic that students struggle with on this paper, so we're going to spend lots of time going through lots of examples. Right, let's get started. So we have question 7 here, so it can be a medium star question, and it says here, by first obtaining a quadratic equation. So that's important. In cos theta, we need to solve the equation underneath. Notice our domain is between 0 degrees and 360 degrees. Now, before I do anything here, I need to know this very, lots of verys there, identity, very important identity, which is that tan theta is equal to sine theta over cos theta. We're going to use this a ton in this video, so make sure that you know this, that these two things are related. So first of all, we're going to take our tan theta and use this identity directly. So wherever I see a tan theta, I'm going to put a sine theta over cos theta. That then gives me sine theta over cos theta times sine theta is equal to 1, like so. Now we're just going to tidy this up a little bit. So notice we have a sine theta times sine theta. You can think of this as over 1. That helps you with multiplying fractions. So that's going to lead then to sine squared theta over cos theta is equal to 1. And now notice, I'm going to read the question here. I want a quadratic equation in cos theta. And at the moment I have it in sine squared theta, which is not quite what I want. This comes to our second very important identity, which is that sine squared theta plus cos squared theta is always equal to 1. A really important identity. There's probably the two most important identities, and these would be it. However, I want to rearrange this slightly, so I want the sine squared theta on its own. So what's the opposite of adding cos squared theta? Well, we need to minus cos squared theta from both sides. This gives us an alternative identity, which is then sine squared theta. This cancels, leaving us always equal to 1 minus cos squared theta. So what I can do now is substitute directly. Wherever I see this sine squared theta, I can replace here with the 1 minus cos squared theta. If I do this, I get 1 minus cos squared theta over cos theta is equal to 1. Now I'm going to multiply by the fraction. Fractions are kind of annoying with equations. So I'm going to multiply the denominator by cos theta on both sides. This cancels. I'm going to continue this over here. So we have 1 minus cos squared theta. We're making progress, which is equal to 1 times cos theta, which is cos theta. At this point, again, it's a quadratic equation. Notice I've got a squared here. So the way to deal with that is make one side of the equation 0. So the way I'm going to do that is I'm going to minus cos theta from both sides. That then gives us 1 minus cos squared theta minus cos theta. And of course, this cancels, so we're left with 0. Now at this point, I'm just going to tidy this up slightly. The first thing I'm going to do is multiply by -1 on both sides. This gets us a positive quadratic to deal with. That means then 1 times -1 is -1. -1 times minus cos squared theta is plus cos squared theta. -1 times minus cos theta is plus cos theta. And multiplying anything by 0 keeps that at 0. Now I'm just going to move things around here. So I've got cos squared theta plus cos theta minus 1 is equal to 0. Okay, so I've got my quadratic equation. In fact, I'm going to write it on the next slide so I can look at it more carefully here. So cos squared theta plus cos theta minus 1 is equal to 0. And now I want to solve this quadratic. Usually the standard way here is to use the quadratic formula, which in Germany we call this the Mitternachtsformel, the midnight formula, because you're supposed to wake up in the middle of the night and say x equals minus b plus minus square root of b squared minus 4ac over 2a. Apparently so. Anyway, we have that here, so I will leave this over here because we're going to use that in a moment. Now remember, these a, b's and c's refer to the coefficients of what we have. So notice we have no number in front of the cos squared x, so cos squared theta, so that's 1, and we have a 1 cos theta here. So if we're going to use the formula here, we have this a being just 1, we have b here also being 1, and our c, our constant term, is minus 1. So to use the formula here, to work out cos theta, we then just substitute these values in. So we have minus 1 plus minus the square root of 1 squared, which is 1, minus 4ac, so minus 4 times 1 times minus 1, all over 2a. That's 1 times 2, which is 2. I've done lots of this at iGCSE. And if we tidy this up, we get minus 1 plus minus the square root of. Now let's have a look at this. So we have 4 times 1 times minus 1. That's minus 4. Then just taking my time going through this, and then that simplifies down to minus 1 plus minus the square root of 5 over 2. So notice with quadratics, we always get two solutions, a positive and a negative. So let's look at these in turn. So let's try and work out the positive one first. So cos theta is minus 1 plus root 5 over 2. And we want to work out theta on its own. So what's the opposite of cosining something? Well, that's going to be the inverse cosine on both sides. This cancels, giving us theta. Then we're going to do the inverse cosine of this lovely horrible fraction that we have here. And this will be the first time we're going to use our calculator. So let's go and work that out. Okay, so I've got my CG50 here. I do like this. It's a graphical calculator. You shouldn't use for A level, but I can do all the functions we need to here. So first of all, we're going to go Shift and inverse cosine. Then we're going to set up our fraction. So we have minus 1 plus, and we want the square root button, so root 5 over 2, close brackets, press enter, and we get 51.827. Again, I usually write down lots of decimal places, dot 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 degrees. Okay, now we'll come back to the other solution in a moment. Notice between 0 and 360. Let's just check if there's one for the negative. So we do cosine theta equals, theta equals cosine inverse of minus 1 minus root 5 over 2. So we want to do the same calculation. This time we want a negative, so we go inverse cosine brackets minus 1 minus root of 5 over 2, and press the enter button, and we get a non-real error. That is very important. So this one here actually has no solutions because it probably goes beyond minus 1, I'm guessing. So this one has no solutions, which is important. So we can discount the negative one. I think it's useful just to go through this. However, we do have a positive solution. So minus 1 plus root 5 over 2 gives us 51.827 degrees. Now we're not entirely finished here because we need to find all solutions between 0 and 360. So I'm going to duplicate this, and let's work out now the other solutions here. So we have one solution. So we have theta as 51.827 degrees, which will round at the end. Now notice with a cosine graph, so if I draw a quick sketch of a cosine graph, we start at 1, we go down to 90, round to 180, 270, and up to 360. So you need to know this graph. We can use the unit circle as well, of course. And we're going between 1 and minus 1, and this is 360 at the end. Now your calculator is not smart enough to work out all the answers that you need between 0 and 360. It's given you only one of them, the 51.827. So if I read that off, so 51.827 be around about here, and this is the value that we've worked out at 51. However, there is some symmetry over here. So if I draw this over here, we've also got this answer here. Now, I'll go through a lot of this in one of my iGCSE videos. You can check that out above if you haven't seen this kind of process before. Also, I've done this with AddMaths as well. So, notice here, this is going to be 51.827 ... degrees. So, this distance between here and here is also equal to 51.827 degrees. So, to work out the other solution, we need to do 360 minus this solution here, 51.827 ... degrees. And again, we're going to put that into our calculator. Now here's our calculator, and all I'm going to do is, well, I've got a non-real error, so let's just delete what we just did before, and we just do 360 minus 51, this answer we just see above, 827.29237, that giving us the second solution of 308.172. So let's write that down. 0.172 ... degrees. Okay, I've got two solutions within this domain of 0 to 360. So my final answers are theta. Now I'm generally going to round this to one decimal place here, so 51.8 degrees and 308.2 degrees. Those are the only two answers that exist for the domain that we're given in the particular question. Okay, and on to part B here. We've got a typical show that trig identity style question. Again, we're going to see lots of these over the course of the video. And we need to show that the left-hand side here is always equal to the right-hand side. So the way I approach this, I usually put down left-hand side. I'm going to write down the left-hand side over sine theta minus sine theta over tan theta. Again, a couple of ways you can approach this. Generally, I'm going to use the identity from before. So tan theta is equal to sine theta over cos theta. Again, wherever I see a tan, I'm going to put sine over cos. So let's pop that in. So we get sine theta over cos theta, now divided by sine theta, minus sine theta over sine theta over cos theta. Okay, at this point we can do a little bit of cancellation here. So we've got a sine theta top and bottom, that can disappear, and then we've got a sine here top and bottom, we can do that. So that leaves us then with 1 over cos theta minus 1 over cos theta. But we can tidy that up here. Again, if you've got 1 over a fraction, a nice little trick here is you can just take the cos theta and bring it to the top. So that gives us 1 over cos theta minus cos theta. The reason that trick works, by the way, is imagine you've got the 1 divided by 1 over cos theta. So I'm just going to write that slightly differently. Then you've got keep it, switch it, flip it, 1 times cos theta over 1. And then that just simplifies to cos theta. Nice little trick to know. Again, this is the kind of thing you want to see in these videos to make sure you can do these things nice and efficiently. Now, we're not quite finished here at this point. We still haven't got this right-hand side. So what I'm going to do here is I'm going to times top and bottom here with the second part by cos theta over cos theta. Now, if you times anything by 1, it doesn't change what it is. So that gives us cos theta times cos theta is cos squared theta over cos theta. The reason we could do that is then we can actually just combine the two fractions. We've got the same denominator. That gives us 1 minus cos squared theta over cos theta. You're probably still thinking at this point, it's not even looking like what I need, but hold the faith. So we can then use our identity from before. So if we go right back to this part, remember sine squared theta is the same as 1 minus cos squared theta. So with that in mind, I can change the top here to just sine squared theta. And now I'll do a nice little trick here. I'm going to separate out the sine squared theta. So again, we can think of this as sine theta over cos theta times sine theta. All I've done is separated out the sine squared theta to sine theta times sine theta. And the reason I've done that is sine theta over cos theta is equal to tan theta, and sine theta just stays where it is, and we get exactly what we want. We've got the right hand side here. Again, a couple of ways you can approach this. I will show you this in the mark scheme, but I think this is the most efficient method. Okay, so you have a look through the mark scheme. So we've got our two answers here, and we've got through our proof, which they've done it in a slightly different way, but still got this idea of sine squared theta over cos theta, which can then simplify down. Okay, and on to question 4 here. So we need to prove this identity, again making it equal to the right hand side. We approach this in exactly the same way as the previous question that we did. So I'm going to write down our left hand side here. So minus sine squared over 1 plus sine theta. And generally the approach, just like we took before here, is we like to create one big fraction, and the easiest way to do that is to multiply these two denominators to get a common denominator. So our denominator at the bottom is going to be sine theta minus 1, brackets 1 plus sine theta. And the way that we work out our numerators here is just doing this times this and this times this. So we get sine cubed theta, brackets 1 plus sine theta. And make sure you've got the minus in there. There is a minus hidden here. So we have minus sine squared theta, sine theta minus 1. We'll leave the denominator for the time being. Let's just sort out the numerator, and let's then see if we can factorize anything out. So if we multiply this together, we get sine theta to the power of 4 plus sine cubed theta, and then we have minus sine cubed theta, minus and minus is a plus here, so we have plus sine squared theta. And again, I'm going to put 3 dots in the denominator. That's not going to change for the time being. Now notice we've got a nice cancellation here, so these two things cancel, leaving us here with sine theta to the power of 4 plus sine squared theta. I'm going to put 3 dots because the denominator will hopefully cancel in a moment. Now notice we have a common factor here. We have a sine squared theta in common, so I'm going to take that out and then work backwards. So what do I multiply sine squared theta by to get sine theta to the power of 4? Well, that's sine squared theta. What do I multiply sine squared theta by to get then sine squared theta? That's going to be equal to plus 1 here. Now if we look at the denominator here, we can actually multiply this out. So we can actually just multiply here by here, 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 and here. If we multiply that out, we get sine squared theta, and we get a plus sine theta minus sine theta, and a minus 1. So we can actually simplify that down somewhat here. This, if we multiply this out correctly, we're going to get sine squared theta minus 1. So let me copy this over, so the progress that we've made so far. So we've got sine squared theta, sine squared theta plus 1, and on the bottom, so where we expanded this out, we've got a sine squared theta minus 1. Okay, so we're certainly making some progress here. So I'm going to take a look at the bottom here. Now remember the identity that we had before, which is sine squared theta plus cos squared theta is always equal to 1. We can do a little bit of rearrangement here. So we can write cos squared theta is always equal to 1 minus sine squared theta. And a nice little trick here, we can actually multiply by minus 1. both sides. That gives us minus cos squared theta. And then we just have to change the signs here. So 1 becomes minus 1, minus sine squared theta becomes plus sine squared theta. And notice this right-hand side is exactly what we have here, just flipped across. So we can actually change the bottom here. And we're making then a little bit more progress to minus cos squared theta. Now this is really, really handy because we're almost there, you can see. And notice that sine theta over cos theta is 1, therefore sine squared theta over cos squared theta is equal to tan squared theta. Notice we've got a minus here, so this entire part here actually simplifies to minus tan squared theta directly. And then we have sine squared theta plus 1, which, let's just tidy this up to look exactly like what we need here. So 1 plus sine squared theta. And we do get the right hand side, which we are looking for. So knowing these two identities about sine over cos is tan and sine squared theta plus cos squared theta is 1 come up again and again and again. And to really get all the marks on these questions, you need to know them and to be able to apply them in unfamiliar situations. Now, a very, very typical question here is this word hence. So using what we've just done, we need to solve this equation. Notice this entire left-hand side here is exactly what we've just been working with. We've shown that this is equal to this. So we can then just replace what's in the box here with what we've just worked out. So we have minus tan squared theta. And it was 1 plus sine squared theta. And even if you don't get the identity question correct, that's not so important because remember here, you actually get the answer to use then in part B. Now, if you multiply out the brackets here, so we get, excuse me, there we are. So we get minus tan squared theta minus tan squared theta sine squared theta is equal to tan squared theta minus tan squared theta sine squared theta. Notice we can't cancel the tan squareds immediately. We'd lose solutions if we do that. And we can notice we've got a minus tan squared theta sine squared theta on both sides. So we can cancel through here, leaving us with minus tan squared theta is equal to tan squared theta. Then what we're going to do, we want to get everything on one side with a quadratic. So at this point, I'm going to add tan squared theta to both sides. That then gives us, well, 0 here because these two things cancel. This is equal to 2 tan squared theta, like so. And let's just move it around slightly. And of course, anything times something to get 0. So the 2 we can just cancel out here. And if we square root both sides, we then get tan theta is equal to 0. So if we think about a tan graph here, again, we should know these ones. It's more or less off by heart here. We get a graph that goes off to infinity and then goes off to infinity again. And we want the zeros here, so we want here, here, and here. Now we're working in radians, so remember pi radians is equal to 180 degrees. So we have 0 here, we have 180 or pi, and 2 pi. Now if we look at our domain very carefully, we can't include 0, we can't include 2 pi, because these are strictly less than signs. So the only answer that we are allowed within our domain is just this answer here. So theta then is just equal to pi radians. After all that very, very hard work for this particular question, we then just get theta is equal to just pi. So you can have a look through the solution here. So this is the identity we look through for 4a, and then notice we get our very last solution. I took this approach here, leading then to theta just being equal to pi. Okay, and on to a much more difficult question here on number 11. So our function we're given here as 4 cos x to the power of 4 plus cos squared x minus k between our domain in radians this time of 0 and 2 pi. and k is a constant, and in this case we're given k is 3 and we need to find the exact solutions. This is an important phrase, which means we're looking for things like pi over 3 or 3 pi over 4. So exact, no decimals here for our solutions. So first of all, we want to make the function when k is 3 equal to 0. So let's just write this out. X minus 3 is equal to 0. And notice it's got parallels with this kind of equation. So if I wrote this just with a y instead, y squared minus 3 is equal to 0. What I encourage students to do, particularly with quadratics, you need more work on quadratics, then please do check out the video above. We can actually factorize this. So if we have a look at this, we can structure this as 4y squared and then y squared. Then we think of the numbers that multiply to give us 3, or minus 3, so minus 3 and 1. Again, order matters here, or we can do 3 and minus 1, minus 1 and 3. We've got all the different combinations. And with a little bit of thought here, we can actually work out what needs to go in here. So having a look at this, which pair is going to give us this plus y squared at the end? Well, I think we need a minus 1 here and a plus 3. Now, if I check that, I notice that's completely wrong because that's going to give us plus 11y squared. So again, this is a sort of trial and error way of looking at this, but it's a very, very effective way of doing this reasonably quickly. And if we actually reverse this around, so if I put a minus 3 here and a plus 1, then if we check this, we can say, okay, 4y squared times 1 is 4y squared, minus 3 times y squared is minus 3y squared, 4y squared minus 3y squared gives me the plus y squared here. So if I transfer this to the question that we have, we can then write this as 4 cos squared x minus 3, and then cos squared x plus 1 is equal to 0. And so if two things multiply to give you 0, then either cos squared x plus 1 is equal to 0. Well, that's not going to work out because if we minus 1 from both sides, notice we can't square root here. Square root of minus 1 gives us imaginary solutions, so this doesn't work. So the only solution will be this 4 cos squared x minus 3 is 0. We add 3 on both sides, cruising here, then divide by 4, giving us this here. And then we want to square root both sides to work out what cos x is on its own. So if we square root, this cancels, giving us cos x. If we square root this side, this gives us the square root of 3 over 4. But we can write this slightly differently to hopefully trigger an exact value in your mind here. So this is the same as the square root of 3 over the square root of 4. Notice there should be plus and minus, which we'll talk about in a moment. And therefore, we're going to get the square root of 3 over 2. And don't forget, we have the plus minus here as well. So we have two solutions, plus root 3 over 2 and minus root 3 over 2. So let me pop that over here. So we have this. And one thing you should be familiar with is some of these exact values. So if I take cos x is equal to root 3 over 2, we should be able to recognize, particularly on the A-level courses, that if we do the inverse cosine of root 3 over 2, this is going to give us pi over 6 as one particular solution. Now again, you can always go to your calculator, and again, make sure your calculator is in degrees at the moment. So if I want to change this, the setup, I come down and make sure this is in radians for this question. So if I did inverse cosine, and then brackets root 3 divided by 2, close brackets. Notice it will give you the exact values as well, so you don't have to memorize these off by heart, but I find that very, very useful to do. Now notice one will find plus and minus, which I'm going to talk about now. So our domain is between 0 and 2 pi. So let's just draw a sketch of cosine. So we start at 1, we go down, and then round, and then upwards, like so. And we've worked out the solution for pi over 6, which is 30 degrees. So that's going to come up somewhere here. Notice we've got a symmetry here over to get this solution. And if this is pi over 6 here, this answer is 2 pi. So to work out the other solution, we need to do 2 pi minus pi over 6. And that's going to give us 11 pi over 6. Fraction skills are very important, particularly by trig. So far we've worked out two solutions. So we've worked out pi over 6 and 11 pi over 6. But we've also got the negative version as well. So we have to consider that part too. Now notice here we've got, so pi over 2, we've got 180 degrees, that's pi, and then we've got 3 pi over 2 as well. Notice we need to think about the symmetry of the function as well. So notice if I drew a line down here, this is essentially the same height as what would be here. If this is pi over 6, this here would also be pi over 6. And then if we did the same thing over here, this would also be pi over 6. I'll go into more detail on this in the add maths video. So notice get the negative solutions, because this here will be negative 3 over 2. And it goes a little bit further to minus 1 here. To work out those solutions, all I need to do here is do pi minus pi over 6, which will give me 5 pi over 6, and then pi plus pi over 6, which gives me 7 pi over 6. So to work out these negative answers, we also need to consider the bottom part and the symmetry of that particular graph. So with this, we've got 4 different solutions here. So we've got pi over 6 and 11 pi over 6 for the positive, and then we've got the negative answers, which gives us 5 pi over 6 and 7 pi over 6 as well. Now we need to use the quadratic formula. This is a nice little mixture of quadratics and trig here to show that when k is greater than 5, this equation f of x equals 0 has no solutions. So let me just start with the general function that we've got here. So plus cos squared x minus k is equal to 0. Now if I was to use the quadratic formula, a is equal to 4, b is equal to 1, and c is equal to minus k. So if I use the formula here to work this out, so cos squared x is equal to minus b, so minus 1, plus minus the square root of b squared, which is 1, minus 4 times minus k, all over 2a, so all over 8 here. And if I tidied this up slightly, we have minus 1 plus minus the square root of 1 minus, that comes 16 times minus k is minus 16k, 2 minuses make a plus, so we get plus 16k all over 8. So using the quadratic formula, this is a general expression. I haven't talked about the 5 yet, but this is the general expression for it. Now, let's think about the situation when we put in k is equal to 5, a sort of border. So it's on that tipping point. So when k is equal to 5, exactly, cos squared x is equal to minus 1 plus minus, well, 16 times 5 is 80, 80 plus 1 is 81, over 8, and that gives us minus 1 plus minus 9 over 8. So that then gives us the solutions here of minus 1 plus 9, which is equal to 8. 8 divided by 8 is 1, and minus 1 minus 9 is minus 10, and then minus 10 over 8. So we have two possible solutions here. So the first one to notice here is when we have minus 10 over 8, notice with a cosine squared function, we expect it to go between basically 1. Generally, a cosine function goes between minus 1 and 1. So a cos squared function, we just want to make sure that it doesn't go beyond 1. And notice here, first of all, we'll take this one first. So first of all, if we try and square root this, this doesn't work. So let's just put that down first of all. Because when we try to square root this, because we want cos x on its own, that's not going to work. And if we take cos squared x is equal to 1 and square root that, then we get cos x is equal to plus minus 1, which is okay. But as soon as we go beyond 5, this number is going to get greater than 1 or less than minus 1 when k is greater than 5, and therefore there will be no solutions. Because remember, with a cosine function, to go back to this graph, again, if I try to work out an answer at 1.5 here, notice it wouldn't actually go through the graph. So our tipping point is at k equals 5. When k is 5, we either get a solution that doesn't work, because we can't square root minus 10 over 8, that does not work. And if we have the 1 solution, then the answer will be plus or minus 1, which is fine, but as soon as we go beyond 5, we'll get an answer that's either greater than 1 or less than minus 1, and therefore there will be no solution there. So you can have a look at the mark schemes, so again, all the solutions that we worked out in the video, and then 11b here. So notice we've taken the quadratic formula, we've worked out the different solutions. I mean, I've mentioned here very specifically that the minus 10 over 8 does not work, which I think you should do in this kind of question. And then notice this idea of cos squared x equals 1. Again, that's fine, but again, anything greater than that will have no solution. Okay, and on to another style question here. So all we need to do here is solve the equation, this time working with degrees. Now, as soon as I see a mixture of sines and coses, again, I'm going to use this idea of sine squared theta. It's always equal to 1 minus cos squared theta. So I'm going to substitute that in, like so. So 6 cos theta plus 1 is 0. To multiply out the bracket, that gives us 8 minus 8 cos squared theta plus 6 cos theta plus 1 is equal to 0. Let's simplify this down slightly. So we've got an 8 and a 1, that makes the 9 here. And we have the rest like so. And generally I like my cos squared value to be positive, so I'm going to switch all the signs here by multiplying by minus 1. Again, I always take a little look in case I can actually factorize it here. Again, doesn't come to me straight away, so I'm probably going to use the quadratic formula. Used it a lot in this particular video. So we have minus b, which is 6, plus minus b squared, which is 36, minus 4 times a, which is 8, times minus 9, all divided by 2a, which is 16. So let's tidy this up slightly. So 8 times 4 is 32. 32 times 9 gives us 288. We'll get a positive 288 all over 16. That then gives us 6 plus minus. What's that going to give us? So 324 over 16 for our cos theta. Square root of 324 gives us 18. So we have a precise answer here, which is very nice. Probably did factorize, but again, quadratic formula also works here. So we get 6 plus minus 18 over 16. So our answers here for cos theta will be when it's added, so we get 24 over 16, which is 1.5, or 6 minus 18 over 16, and that's going to give us minus 12 over 16, simplifying to minus 3/4. Now notice this answer can't work because this answer is greater than 1. So we have one solution here. So we have cos theta is equal to minus 3 over 4. So then we can work out theta here by doing the inverse cosine of minus 3 over 4. So let's see what our calculator says here. So we have cosine and minus 3 over 4. Okay, and that gives us 138.59. Degrees. And if we think about a cosine function, I always draw a quick sketch to see if it makes sense here, which it does. So we have 90, 180, 133. It's going to be over here somewhere, which makes sense. And because our domain, notice here, is just between 0 and 180, we have no other solution that lies in this box. So that's our only answer here. Theta is equal to 138.6 degrees to 1 decimal place. Okay, so you can check the answer there and go through the solution. And if you need to get your functions up to scratch for all of A-level maths paper 1, then check out the video right in front of you because you'll find that's really, really helpful. And if you want to go through a general playlist of all paper 1 material, then check out the playlist also right in front of you as well.